Hello and welcome to LittleBIGPhysics, a series in which we try to figure out the mechanics of the world of Little Big Planet from the ground up. Last time, we took a closer look at air resistance by examining its effects in zero gravity. Today, I want to get back on track with exploring how objects move and react to things happening to them. More specifically, I want to look into what happens when two objects collide with each other. Let's set up a concrete scenario. We have two large trucks zooming down the road towards each other at high speeds. We know how fast each one is going, but they're not necessarily moving at the same speed. What happens if they run into each other? We're going to want to simplify this scenario to make it more consistent and easier to measure. Instead of driving along the ground, let's have both bodies sliding along a surface. Glass is super slippery, as you can see here, so we'll make both the ground and the objects out of glass. As for the shape of the two objects, let's make them both squares so that they collide head-on, instead of one bouncing up into the air or anything crazy like that. It'll be easier to analyze the situation if everything stays on one horizontal line. To get the blocks moving, I'll attach mover chips to them, which allows me to set the speed to whatever I want in in-game units, which you can convert into lengths per second if necessary. Since we don't want the movers affecting the blocks after they collide, the blocks will pass by a checkpoint that turns the movers off shortly before colliding. To monitor the collision quantitatively, we'll put a speed sensor on the blue block on the left, whose reading will be displayed above. A reading of 1.0 on the display will be 100 in-game speed units, or about 125 lengths per second. What happens if we slide both blocks into each other at 10 in-game speed units? They come to an immediate stop upon impact. Intuitively, this makes sense. The scenario was completely symmetrical to begin with, and it ended completely symmetrically too. What if we leave the red block motionless as the blue block crashes into it? The blue block takes the red one along for a ride. It's hard to be 100% sure since the blocks are slowing down as they slide across the glass, but the speed of the blue block seems to be cut about in half once it hits the red block. Moving the checkpoint onto the side of the red block makes this a bit easier to believe, as the blue block's speed is initially 10 speed units, and then 4.99 speed units. Though, rather curiously, the reading oscillates a bit if you look at it frame by frame. There could be a few reasons for that, like how the speed sensor actually determines speed, or the initial collision somehow slowing down the block before it speeds back up again, though the latter seems unlikely. It also might have to do with how Ford's signal display works. I admittedly have no idea how it does what it does. Unfortunately, this introduces an element of guesswork into our readings. I think I'll just take the number after which the reading begins to drop more slowly. Let's look at the next trial frame by frame, for instance. What if both blocks are moving, but the blue block is moving twice as quickly? Reviewing it frame by frame, the reading goes up and down by a few units before dropping more slowly from 4.99. Thus, it looks like the speed drops down to 4.99, about 1/4 of the speed before the collision. The oscillations seem reproducible, by the way, as running the test again shows the exact same sequence of numbers every time. What if you repeat this test, but double the heaviness of the blue block? I do so by making it twice as thick. It's a little harder to make out the speed this time, but it seems to be 11.39 speed units. That seems like a strangely arbitrary number compared to what we've seen so far, though. To make sure we have all our bases covered, I also ran the same trial again with both blocks moving at the same speed, so the only difference is how heavy they are. When we do that, the speed drops down to about 3.3 speed units. And if the second block isn't moving at all, about 6.6 or 6.7 speed units. These ones are interesting since they seem to be multiples of 1/3. Now let's make the second block the faster one. What if the blue block is twice as heavy, but the red block moves twice as fast? About 1.4 speed units, another number that seems kind of random. Now, before we go any further, some of you might have had a better idea for how to keep the blocks from slowing down than putting them on a slippery surface. What would be much better, of course, is not having them on any surface at all. Thus, we probably should have been using anti-gravity modifiers this whole time. It's never too late to improve our methods, and I suppose this is a good example of the learning process that one must face when the answers aren't already known. No worries though, since we can just repeat the trials we've done. Now that the blocks will slow down way more slowly, we can read the final speed much more easily. Two blocks with the same heaviness and speed still results in both stopping. Doubling the speed of the blue block still ends in the blue block's speed dropping down to 1/4 what it was before. The blue block being twice as heavy and the red twice as fast ends not in 1.4 speed units, but 1.33, which seems like a more significant number, since it's 2/15ths of the original speed of the heavier block. For something new, we can make the red block 4 times as heavy and the blue block 4 times as fast, but that gets us another seemingly arbitrary number, 2.4 speed units to the left. At the risk of getting repetitive, I also ran the same trial again, with the blue block moving at 44 speed units, which gave it a final speed of 1.6 speed units leftwards, and I also ran it at 50 speed units, which gave a final speed of 2 speed units, this time to the right. But where are we going with all of this? Well, I admit that the tests were somewhat haphazard. It probably would have been much better if we had a bunch of trials where we only changed the heaviness of each block, and another bunch where we only changed their speeds. Unfortunately though, since things work out to where collecting the data and analyzing it are months apart for me, we have to work with what we have. Our end goal, like usual, is to develop some kind of consistent rule that will predict what happens in these scenarios. One rule that seems to fit the results of a lot of these tests is the following. This says that for 2 blocks that bump into each other and stick to each other, their speed after colliding, the part on the right, is equal to the expression on the left, which takes how heavy each block is, multiplies it by how fast it's moving, and adds those 2 numbers together, and then divides them by their combined heaviness. Just like the display that we had in our tests, we'll also say their leftward speed is negative. For example, for the first test we ran, the blue block was moving at 10 speed units to the right, so it had a speed of positive 10 speed units, and the red block was moving at 10 speed units to the left, so it had a speed of negative 10 speed units. We can just say that each block was once mass in heaviness, since it turns out that all that matters is the ratio of their heaviness to each other. If we put all that together on the left side of the equation, we get a speed of 0 lengths per second, meaning that they stop after hitting each other, just like we saw. What's the idea behind this equation though? We can try to use it, but how do you come up with it, and what does it really say? There are 2 aspects to this equation on a conceptual level. What affects how easy or hard it is to stop a moving object? Imagine something that would be hard to stop. What's it like, and how is it moving? Objects that are hard to move are heavy and move fast. The heavier they are, and the faster they move, the harder they are to stop, so the more easily they can knock something out of their way. We can't add together a block's heaviness and its speed because they have different units, but we can multiply them together. Thus, we might model the difficulty to stop of an object as m times v, its heaviness multiplied by its speed, and the higher this number is, the harder it is to stop. Increasing either the heaviness or the speed of the object will increase this number. Notice that since the object's speed is in a certain direction, its difficulty to stop is in that same specific direction. This makes sense. Imagine a heavy ball rolling in a given direction. It might be hard to push on it opposite the direction that it's moving to get it to stop, but giving it a shove sideways to deflect it isn't nearly as hard. Now then, what happens if 2 objects hit each other and stick together, like the blocks in our experiments? As a guess, the difficulty to stop of the 2 objects stuck together might be the sum of the difficulties that each object had before colliding. Hence, m1 times v1 plus m2 times v2, where m1 and v1 are the heaviness and speed of the first block, and m2 and v2 are the heaviness and speed of the second block. We can call this idea of difficulty to stop momentum. An object with a low momentum is hard to stop, and what we're theorizing here is that if 2 objects collide and stick together, the momentum of the 2 of them stuck together is the sum of their momenta from before they hit each other. Having established that, let's move on to the second aspect. We're trying to find the final speed of the blocks stuck together, which should be in units of speed. Right now though, our sum of momenta is in units of heaviness times speed, which in our preferred units would be mass length per second squared, which isn't what we need. So we can just divide by units of heaviness, and then we'll have the units of the speed that we want. What heaviness do we divide by though? A good guess would be the sum of the heaviness of each of the 2 blocks. That way, if a block runs into another very heavy block, the combined momentum will be divided by a big heaviness, giving it a small speed, which is what you'd expect from something hitting something much heavier. On the other hand, if the 2 blocks had similar heaviness, the final speed would be higher. This gives us the equation that we're going to test out. Let's see if the equation can predict the other results that we got then. What about when the red block wasn't moving? Everything stays the same, but the red block's speed is now 0, so the equation becomes this. This time, we get 5 speed units, pretty much exactly what we got in the test, which is 4.99 speed units. We get the same answer again if both blocks are moving, but the blue block is moving at 20 speed units, while the red block moves to the left at 10 speed units, just like in the next test. Strangely, it's actually off by a little over 1 speed unit for the test where we doubled the thickness of the blue block, which makes me wonder a few things. The equation that we put together could be wrong, of course, or it might be that things just get a little weird when you start changing the thickness of the blocks. It's hard to tell for sure just yet. Setting the speed of the red block back to 1 speed unit gives us 3.33 speed units as our final speed, which is just about what we got in the experiment, and setting its speed to 0 matches our results yet again, with 6.67 speed units as our answer. But when the blue block is twice as heavy and the red block is twice as fast, we run into a problem again, where we expect a final speed of 0, but the final speed in the experiment was a bit over 1 speed unit. This also happens when one is 4 times as heavy as the other, and the other is 4 times as fast. We expect 0, but we get a speed that's different by just a few speed units. Even worse is that when one blue block at 44 speed units collided with 4 red blocks at 10 speed units, the equation says that the final speed should be 0.8 speed units to the right, but the final speed was actually 1.6 speed units to the left. But on the other hand, when we changed the blue block speed by just 6 speed units to 50, we got exactly what the equation predicts, 2 speed units to the right, strangely enough. So our model seems to be right most of the time, but wrong pretty often too. Is there any pattern to its mistakes? Whenever the equation is wrong, the experiment's result went faster in the direction that the heavier block was initially traveling. For example, when the blue block moved twice as quickly and the red block was twice as heavy, the equation predicted a final speed of 0, but the final speed was actually just a little to the left, the direction that the heavier block, that being the red block, was initially moving. If we give the equation the benefit of the doubt, I have an idea about what might be happening here. The movers are supposed to be turning off before the blocks collide. If you look at the video though, it looks like the tag sensor always activates on either the same frame the blocks collide, or the frame after. What if the sensor was activating and turning off the movers just a little too late? What would happen then? Here's my reasoning. Intuitively, you have to push harder to move something that's heavier. We haven't been saying anything about how hard the movers are pushing on those blocks though. Movers do have a strength setting, but we have it set to 100% on both blocks in every trial. Instead of worrying about that, we just set the mover to the speed we want and it pushes as hard as it has to get there. But what if 2 movers were pushing against each other in opposite directions? It stands to reason that the movers would move in the direction desired by the mover that pushes harder. So if 2 blocks hit each other, they'll probably move together in the direction desired by the mover that pushes hardest. But which one pushes the hardest? Well, if we're right about having to push harder to move heavier objects, the mover on the heavier block must be pushing harder, as long as the mover on the lighter block isn't trying to go way faster to offset the difference in heaviness. Thus, if the movers don't turn off in time, the final speed of the blocks will usually favor the direction that the heavier block was initially moving in. In other words, I might have botched the experiment by messing up the tag sensors. Well, can't we just fix that and try again? Unfortunately, I haven't had access to my PS3 for a while since recording this, so I can't do that right now. But what we can do, using footage I've already recorded, is investigate whether it's really true that one has to push a heavier object to get it to move the same way as a lighter object. If it's true, then that will serve as evidence in favor of the momentum model that we've built so far. If it's not true, we'll just come up with something else. Then, once we have it all figured out, we'll have our answer for what happens when those 2 trucks collide. Figuring out the world around you isn't always straightforward. There's some guesswork, there are some mistakes, and there's always something new to try out. Right now, we're considering this concept of momentum to explain what happens when objects hit each other, but we've run into some obstacles. Even if we're right, though, what about when 2 objects bounce off each other instead of sticking like they did in our experiments? Will it still be correct then? We'll have to face those questions when we get to them, but for now, we already have our plates full of hypotheses to test and experiments to rerun anyways. I'll see you all again when we test out whether we're really right about heavier objects being harder to push. Until next time, and stay curious.